Now, let's talk math. In math, you guys deal with numbers. Okay? Numbers are imaginary. Nobody's seen 3. Nobody's seen pi. Okay? They're all abstract things. In the sciences, we use the numbers to represent something. And size, we call magnitude. I don't know if you've heard that term before or not. Yes or no?
Yeah.
Okay. So size, magnitude, sign is going to tell you, positive or negative, and those things have meaning to us. But how we say it sometimes may contradict what you're thinking in terms of pure math. Like to me, negative 10,000 can be a very large number. On a number line, though, negative 10,000 is really small, right? Because it's less than 0. So we need to get, lay some groundwork here so we understand how we're using some terminology to make it a little bit easier to understand when you read something or I say something, okay? So, is negative 10,000 a large number, a small number compared to negative 10? Depends. In pure number-wise, just math, it's what? It's smaller. Okay? Is negative 10,000 a large number, a small number compared to a million? Well, again, number-wise, it's a really small number compared to a million. Positive a million. But a negative 100 is less than 100. Right? So, this is something that's going to be really important when you take physics. Do I have any sophomores in here in physics?
Yeah, you can do it. You can
Yeah.
do it. It's painful, but you can do it. So one of my friends is serious.
Actually, I have plenty of people do it, no problem.
No, it sounds very well.
Okay, so positive and negative represent a measurement of direction. In physics, that's going to be, are you traveling east or are you traveling west? I mean, you have a starting point, okay? For us, it's generally going to be, is something gaining or is something losing? I mean, both of those can be large values. It's just what direction are you going? Okay? We have to have a starting point. And based on that starting point, how is the change occurring? That's what makes it a little bit different than just pure numbers. That's why I said negative 10,000 for us could be a very large number. Because if I lose 10,000 joules of energy, I've lost a lot of energy. I could also gain, because that's a negative number. We would assign that a negative value. I could gain 10,000 joules of energy. That's a very large value. The positive and negative sign are simply telling us what direction the change is. That's why we talk about magnitude. Magnitude, I know you guys have talked about absolute value. Right? Little vertical bars. You know what I'm talking about, right? Okay, so that's the magnitude. If I put vertical bars around a negative 10,000, okay, we just talking about 10,000. That's a large number. So a lot of times we have a negative or positive sign on the number, but we speak to each other about the magnitude of it. On paper, though, you have the negative or positive sign so you can designate whether it's being lost or gained. Does anybody have any questions about that? Okay. So the equation that I have on this slide here, the V equals K Q1 Q2 divided by V. This is an equation that is really, really important for us. We're going to revisit this equation throughout the year, because this equation tells us how strongly something is going to attract or repel. Okay? Now, K is a constant. That numerical value we really don't care about. Q1 and Q2, these are going to represent the charge. For example, what's the charge of a proton? Positive what? 1. So if I was dealing with a proton, I would put either Q1 or Q2 as a +1 value. So the numerical value that you're assigning the charge for. D is distance. How far apart are the particles? V is the potential energy. Now, I know in middle school, you guys talked about potential energy of motion, essentially, right? You have a rock at the top of the hill. It's all potential energy. If you nudge the rock, it's going to roll down the hill, and that potential energy changes into kinetic energy. This potential energy is the potential energy that the molecules or particles have due to their attraction or repulsion. We'll talk more details about that here as we go. I don't know if I said it, but I'm going to say it again. You don't need to memorize that equation. I will give it to you. And generally, this equation is used mainly to look at the mathematical relationships, not to solve. I think I may have you use it to solve for a value maybe 2 or 3 times. But other than that, it's there to show us that there's a relationship between the charges and the distance. That's the key. So if you were to increase the distance, what would happen to your V, the value for V? It would go down. Okay? All right. If you increase Q's, what would happen to V? It would increase. If you can do that, that's really all we're going to do with this equation. But those relationships are really, really, really important for understanding what we're going to do now and throughout the year. Because in the end, chemistry is really a lot of it is really about how do these molecules attract each other? How do particles attract each other? Okay, so I kind of went over this already. V represents potential energy between charged particles. Translate to how strongly the particles are attracted or repelled. So it's not always an attraction. Sometimes you got repulsions. K is a constant. D represents the distance between the particles. It will always be a positive value. Okay? In physics, you may have a negative distance, but that would be because you're changing distance. We're just measuring a distance. Okay? So that for us has to be a positive value. Q can be positive or negative because we have positive or negative particles. Our positive particles are what? Protons. Our negative particles are what? And that's pretty much it. Our polyatomic ions that we dealt with, they have charges, but that's because they have either more or less electrons. Okay, so everything about charge for us is going to revolve around those protons and electrons. How many do you have? And like I said, we're rarely going to use this to solve for any equations. Okay, magnitude. Absolute value of the number used to measure quantity. Anyway.
So if Q represents the charge of an atom, can it just be equal to 0?
It could for the atom, yes. Because the atom doesn't have a charge overall. We'll talk more about that in second semester, that atoms, individual atoms, can have an imbalance in that charge because the electrons move around. Okay, but we'll save that for second semester. Okay. All right, assuming that Q1 and Q2 remain constant, you guys have already answered this, but I'm going to do it again. What happens to the magnitude of V as D is increased? Magnitude. If D is increased, V is going to do what? Decrease. The magnitude is going to go down. The reason why I said magnitude is because V could be negative, right? V can be a negative value. And if the value magnitude-wise decreased, the number's getting smaller. Okay? Okay. If the two particles are separated by an infinite distance, what value does V approach? Jordan.
0.
It approaches 0. Does everybody know why? Think magnitude here. Jordan?
Because I think the line size enemy is going to start approaching 0, just ignoring it as a large one.
So think about number line, right? Okay. If D is increasing, the value for V, you just got done saying, the value for V is what? Magnitude. It's decreasing. So, okay. I want to go back and revisit one of the things I said. So V equals K, Q1, Q2 divided by D. So, I'm just going to make K equal 1. Just to make the math easy, I'm going to make Q equal plus 1. I'm going to make Q2 equal negative 1. And I'm going to make D equal to 10. That makes math easy, right? So, if I were to set up and calculate V, I'm going to have 1 times negative 1 divided by 10, which would equal what? 110, or 0.10, but negative. Is everybody okay with that? Okay. Now, I'm going to change the distance to 100. So V is going to equal 1 times negative 1 divided by 100, which is going to be 100th, right? Or negative 0.01. What happened to the value of V? Did it go up or did it go down? Did it go up or did it go down?
Numerically, it went up.
Magnitude.
Magnitude, it went where? Down. Number line, it went where? Up. Okay? If I change this, and I make this positive, okay? What happens?
The one on the left is, greater than the one on the right.
So now it's going where?
Oh, down.
It's going down. In both cases, though, with the negative, it's increasing and getting closer to what value? 0. When it's positive, it's decreasing, getting closer to what value? Say it. 0. And Jordan, that's exactly right. We're going to approach 0 no matter whether we're on the positive side or negative side. Everybody okay with that? This is what makes using math and science a little bit different than what math is just alone.
So the first one, the magnitude still went down, but it got larger.
Exactly. That's why I wanted to make sure that we had the magnitude versus the the actual size thing laid out. So, as distance approaches infinity, our value for v is going to approach 0. D is finite, so it's not infinite, okay? Particles have the same charge. Q1 and Q2 are the same charge. Is V greater than or less than 0? Or does it depend? Abby? Greater than? Why? Okay, so this is your, remember in middle school when they gave you those really long butt questions where you had like -2 plus of 3 times -5 times -3 divided by, remember where they had a whole bunch of negatives and positives just try and confuse the hell out of you? When all you had to do is count up how many negative signs that you have, especially if it's multiplication and division. And if there's an even number of negative signs, it had to be positive. If you had an odd number of negative signs, it had to be negative. It's as simple as that. When you add addition and subtraction in there, things get a little bit goofy, but we don't deal with addition and subtraction very often. So you're absolutely right. If both of them are positive, we know it's going to be positive. If both of them are negative, negative times negative is positive. So it doesn't matter. If both of them are positive, both of them are negative, it's going to be greater than 0.
Okay, so I'm probably having big dumb moment.
You're not having a big dumb moment.
So, doesn't it depend on
K is always going to be a positive value. I don't think I had that in the slide, did I?
No.
Okay. K is going to be a positive value.
Does finite mean positive, or does it just mean not?
Well, distance for us is always going to be a positive value.
Oh, I have
Finite is simply because we don't want it to be 0. And we, as Jordan said, you know, if it's infinite, then our value is essentially 0. Okay? Other questions for clarification?
Wait, so 0 is not.
Zero is a 0. What I'm talking about with distance, you know, distance is infinite. If it's big enough, the value for V is essentially going to be 0. All right, Q for an electron is -1. Let's fill in the blanks here. Q for a proton. Come on, you guys already answered this once. Q for a proton. +1. Q for a neutron. 0. It's neutral. Q for a carbon nucleus.
Wait, 6.
+6.
+6. Look at the periodic table.
Yes.
Now, so I can't remember. Ava, was you asked about the atom being 0?
Yeah.
Okay. So, if carbon has an equal number of protons and electrons, the atom itself is going to be a charge of 0. But I'm being specific here about the nucleus only.
And the nucleus is no electrons, so they'll just do whatever.
Exactly. So the number of protons that you see on the periodic table, that atomic number, is going to tell you the charge of the nucleus. It doesn't matter how many neutrons, because you just got to tell me, neutrons have what charge? 0. Questions? Okay, recall that a hydrogen 1 atom consists of 1 proton in the nucleus and 1 electron outside of the nucleus. Remember what that superscript 1 means, right? Somebody tell me? Rupesh?
Atomic number.
No,
Oh, mass number.
mass number. Which is, mass number is what? What? Protons and neutrons. So if it's hydrogen 1, there's only one thing in the nucleus, and that is what? The proton. So recall, hydrogen 1 atom consists of 1 proton nucleus, 1 electron outside the nucleus. Is the potential energy, V, of a hydrogen atom positive or negative? So if you were, I don't care what the D is, it's going to be a positive number. I don't care what K is, it's a positive number. I'm not asking for the number, I'm asking for the sign. If you have a hydrogen atom made up of a proton and made up of an electron, is the value for V going to be positive or negative? Ava?
It's going to be positive, because even if it has a equals 0, that's not negative.
How are you getting a positive value?
I'm not, I don't know the number,
What's that?
because you don't have negative numbers, so.
You don't?
No, because your hydrogen doesn't have a negative charge. So,
It doesn't?
no, because you have your proton and you have your electrons.
Oh, stop. You said. You have a what?
You have a proton and you have an electron.
What charge is an electron?
Oh, wait, what?
What charge is an electron, class? Negative. So I wanted you to reason it out there, Ava. That's why I was thinking you through those questions. Okay? So you have an electron and you have a proton. if you plug the values in for the charges of those into that equation, remember I said I don't care what K is, and I don't care what D is. I'm not looking for a number, I'm looking for a sign, right? If K is always positive, D is always positive. Proton, okay, there's Q1. We'll call it Q1, proton. Charge is what? 1. Q2, electron with charge. And plus 1 times negative 1 is? So our V has to be negative value. Ava?
I thought Q represented like the atom. Where'd you get that Q equals, so first Q equals 1?
So it depends on what you're defining Q to be. You're right. If I was talking about an atom in total, Q would be 0.
Oh, okay, so you're asking for the whole atom, so you gotta split the...
Exactly. So you got to split them apart. So you got protons and you got electrons separate from each other, right? Okay. Does the value of V from the previous answer represent an attraction or a repulsion? Lexi, you were going to answer and then you changed your mind. What were you going to say?
I'm just not sure, because I don't know whether attraction is positive or negative.
Forget that. Don't worry about whether it's positive or negative. Is there an attraction between the electron and proton in the hydrogen atom? What would be repelling?
The positive and negative, there's separate charges.
Whoa, time out. Time out. You have a positive and you're negative. They're repelling?
No, wait. So they are attracted to each other, because
Yes.
the negative cancel out.
Yeah, okay, so the total thing cancels out. But here's the key. Here's the key. V is negative, right?
Yes.
You have a positive value for the proton. You got a negative value for the charge of the electron. You guys know what do opposites do? They attract. What does a negative value for V represent? So we said that the proton and the electron together in this equation give us a negative value. And we just established, based on the discussion with Lexi, that there's an attraction between the proton and the electron. We know that because, nature, opposites attract. Here we're putting a mathematical value to that. It's a negative value in the equation. So a negative value represents an attraction. So if a negative value represents an attraction, what would a positive value be? Repulsion. And the only way, I'm going to go back, the only way you could get a positive value is if what were true. Abby, they have to have the same charge. Or sign, I should say. Okay? So if your Q1 and Q2 are both positive charges, positive and positive are going to do what to each other?
They're gonna repulse.
Not attract. They're going to repel. So there's repulsion. If you have a positive and a negative, they're going to attract. And if you have a positive charge and a negative charge, V has to be negative. So attraction is a negative potential energy. A positive is going to be when both Q1 and Q2 are both have the same sign. So a positive times positive is going to give you a positive value. A negative times a negative is going to give you a positive value. And if they have the same charge, they are going to do what to each other? Repel. So what does the value of 0 represent? Rupesh? No attraction and no repulsion. There's no interaction. Now, Brooke, go ahead. I'll answer your question. I want to add an addendum to that.
But does it also mean that V is infinite? Or is this another?
Okay. So that was your question relates to my addendum to this. And this is where you get into the deep thought about math. Can V ever be 0?
No.
No.
Get close.
It can approach 0, but it's not going to theoretically. Okay, so this is where we differentiate between theory and reality. In theory, mathematically, V cannot be 0. In reality, though, we reach a certain point at which the value is so small in magnitude. The value is so close to 0 that in effect, the value is 0. Ava?
Can you just plug in the right numbers and then it'll be 0?
Nope. No way you can do it.
Oh yeah, it's 4 by the
So, if particles, like if Q1 uses a neutron, wouldn't it have a charge?
In that case, you would have a 0. But that would be the only time you would have that. And we really don't care about neutrons because they don't contribute to the attractions that we're talking about. But you're right. That's why neutrons were so hard to discover in the first place. I mean, we knew about protons and electrons 30, 40 years before we knew about neutrons. In fact, it was less than 100 years ago that we discovered neutrons. Because they have 0 charge, they don't interact with stuff. And if you think back to the experiments and stuff that we looked at in the first week of school, they were all based around attractions and repulsions. You had the charged plates. Is it going to a positive plate or is it going to a negative plate? So without the charge on something has been very, very important in discovering stuff. Now we have different things we got to do. With neutrons, had to take a different route. So, positive represents repulsion, negative represents attraction, 0 represents no interaction. And besides having a neutron, in reality, you can get to a 0 if the distance is large enough that the value for V is so insignificant we just ignore it. Who likes playing with magnets? You ever tried to get a magnet? You got to get a strong magnet. It's more fun this way. Get 2 magnets, or get a magnet in the refrigerator. Try and get them as close as you can to each other. You know what I'm talking about? And with really strong magnets, it's hard to do. Because what are you doing to the distance? You're decreasing the distance. Which would what would happen to V? The magnitude, let's say magnitude. What's going to happen to the magnitude of V?
A lot stronger and a lot bigger.
It's going to be bigger. The value for V is telling you how strong is that attraction or how strong is that repulsion. Now, the reason why I said magnitude is because if it's an attraction, it's a negative value, right? So as you bring those two magnets closer and closer and closer together, V is getting more and more and more negative. On a number line, that means it's getting what? Smaller. But for us, remember, this is the difference between just pure math and how we're applying the numbers. That number getting smaller and smaller and smaller and smaller on a number line means that our attraction is getting what? Stronger and stronger and stronger, because they're getting closer and closer together, harder and harder to pull apart and keep apart. Eventually you get so close that they just snap together, right? Questions?
You guys should make magnets like
Say again?
You guys should make magnets like connects. What?
They snap together, yeah. It's like,
It's never happened to me.
I'm talking about when you can't put this together.
So bring south and south or north and north. Now so I'm talking about when you hold the magnets together, you try to keep them from coming together, from attracting.
Oh no.
Okay, reverse it. Now you try to push magnets together. So you try to bring the north side to the north side, or the south side to the magnet. And you have to actually push. I mean, you can get them to, you can push hard enough if you're, if the magnets are weak enough, you can push them together and make them contact each other. But you have to hold them that way, right? Because the repulsion is getting really, really, really high, because they're getting really, really, really close. So when we say that an attraction is very strong, that means the magnitude is going to be large, but the sign is going to be negative. And a repulsion that's very strong is going to have a large magnitude with a positive sign. Take those two magnets that are really, really hard to keep together or really, really, really strongly attracted to each other, depending on what side you're using, when they're close, and then put them on opposite sides of the room. Is there really any interaction between them when they're on opposite sides of the room? No. Their V, their interaction would essentially be what value? 0. So when we talk about our infinite distance, it's kind of relative to what we're talking about. If I had sensitive enough equipment, would I be able to detect the magnetic field of a magnet that's over there from the back of the room?
Yes.
Yeah. But it's going to be teeny tiny. Okay? Who's got questions? Tristan.
Okay, hold on. Would this equation technically equal 0? Okay, so if you had V equals Q or K, Q1, Q2 times 10 to the negative infinity, wouldn't that technically make V equal what the closest thing to 0 is?
Eventually, that's where you get the calculus. Okay? All right. Number 4. Brooke?
You don't like color.
You know what? When I made all these, we used to have the projectors and color just never did come off very well. So it's not that I don't like color. It's just,
You're not having it.
yeah, I mean, it's mostly text. That's why I have you guys, take the notes and really you can color it up all you want with your highlighters and stuff. Make it pretty. Okay, so a couple of goals in this unit are for us to, how is an atom, how do they work? What are the attractions and repulsions? Things like that. But another part of it is to look at how science works with the development of stuff. I mean, science, I've heard it said that science never really stops because you're always finding something new or you're always questioning something. To this day, we keep testing and studying the atom and the structure of the atom. And was, Einstein right? And we already saw Bohr was wrong, right? Bohr's model worked for hydrogen, worked perfectly for hydrogen, but you try to apply it for helium, not so much. And any other element that had more than 2 electrons, it just crumbled apart. Not to say that Bohr wasn't important. He was really important. There were pieces of his model that we use to this day, dealing with the spectrums and stuff, and the basic idea of the electron being quantized. It has to have a specific amount of energy. So the development of the model of the atom still progressed using what we call a planetary model. Okay? And there's some aspects of the planetary model that aren't completely incorrect even now. I mean, we can say that we expect a distance away from the nucleus for an electron. It's not going to be a guarantee that it's going to be that distance, but there's an average distance where we would expect them to be. Problem is, the electrons, we know now, don't go around in little circles. If we want to jump ahead, how do electrons exist around the outside of an atom? In orbitals, which are what they're called, but all those orbitals together make up a what? A cloud. Okay? Now we'll get to that point. All right? But how do we get to that point? We have to do experiments. We have to set up and say, okay, this is what we're observing. Let's try to explain it and then test the hell out of it and see if it works. And when it breaks, we go and figure out, okay, what broke, what was wrong. Okay? So, we've got our Coulombs Law. That's the equation that we have been using. Okay? So we know ionization energy. We can remove electrons from atoms. We saw that last time in class with the photoelectric effect. This is a little bit different in that we're removing electrons from atoms, not a group of atoms in a solid metal. Okay, so it's a little bit different. Electrons are considered to be removed when the energy, the potential energy, approaches zero. We're at that infinity point. And I'm not going to pull it up, but you could go back and look at that Bohr model that I had with the lines on it, with the arrows showing the jumps, and you would see that they had an n is equal to infinity on there. There is a certain distance away from the nucleus where we would consider the electron no longer to be affected by those protons. That means that the attraction is going to be zero. That would represent a free electron. It's not contained in an atom. Okay, so here's our scenario. We've got 3 atoms here: atom L, atom Q, and atom T. In atom L, there's a distance between the nucleus, which has 1 proton, and 1 electron. Distance between them is 100 or 1,000 picometers. And this says that if you add 0.231 times 10 to the negative 18th joules, that will remove the electron. Now, I understand there's scientific notation there looks a little weird because they don't have a number to the left of the decimal point, but there's reasons that you would do that.
I know the reason.
What?
You're lazy.
What's that?
The reason you wouldn't do do that is if you're lazy.
Or if you want all of the exponents to be the same.
Yeah.
So like if you're lining up numbers,
So you're lazy.
no, not lazy. You're being smart about it. If I wanted to compare numerical values and where they were in scientific notation,
Yeah.
what throws people off is that they don't look at the exponents. So if I had like 0.231 times 10 to the negative 18th, and I was comparing it to like 1.5 times 10 to the negative 18th, which one's bigger? The 1.5 times 10 to the negative 18th. If I put that in correct scientific notation, it's going to have 2.31, and people look at that very first part, and they're going to say that 2.31 times 10 to the negative 19 is greater. No, it's not. Right? So there's reasons why, and it's not because they're lazy. Although
The reason I would
that right,
is
okay,
because I'm lazy.
okay. All right, atom Q has a distance of 500 picometers. Its ionization energy is 0.462 times 10 to the negative 18. Atom T has a distance of 200 picometers, and its ionization energy is 1.16 times 10 to the negative 18. See where you've got that now? We can compare those more directly. Which one requires the most energy to remove the electron? Atom L, Q, or T? Atom T. Why? Why does it require more energy to remove that electron? Distance is small. Ava?
Ionization energy is just how much energy you gotta put on the atom to go live.
Yep.
Okay.
Yep. So the ionization energy is how much energy is it going to take to remove that electron? Can somebody tell me what the sign on the energy for the ionization energy has to be?
Positive.
It's got to be positive. Okay? Because what is the V value, the potential energy for the attraction between the proton and the electron? It's negative. And you're trying to get them to be, to remove the electron, you're trying to get V to be what? Nope, not positive. Zero. So if you have a negative value for V, for the potential energy, you have to put energy into that, a positive value, to get to zero. Once you're at zero, now the electron's free. Okay, without using a calculator, predict what trend you expect for the values of V for these hypothetical atoms. What do you predict the trend is going to be? Discuss that at your tables. I want somebody to designate a spokesperson from the table, and I will choose a group. I'll give you a hint. I'm probably going to choose a group that hasn't had anybody at the table speak yet. Oh, you can discuss it. What's your thoughts?
But it's not the same. Oh wait, no, it is. It's just.
Because you never truly close enough. Ionization. Ionization. Entitled ionization. So how much energy is required? It's not infinity.
No, Alex. It's
I have math.
just
So what's the
I got no one cares.
I didn't even see that.
You should have did your math homework at home.
I just
Well,
Yeah, but didn't.
but
we haven't even.
it's going to have that. But what does he tell us?
Okay, well, they need to forget this stuff. That's tough. Okay, and this is
Or measure it. So if it's negative, what is it? Well, it's not necessarily going close to zero. Negative, but it's got about.
Can you guys so if Q2 or 1, so let's just forget 5,000. 5,000, that's enough, right?
Well, the only way we're approaching
And if you find 2,000, that's a different number.
So I'm starting off with if it's positive, you said if it's negative,
You don't need to.
distance affects.
Rotation equals 1, and then Q1, Q2 equals 4.6 times
What's happening
equals
with this?
5,000. Didn't know what
So what would that do to the attraction?
AP book physics.
Right. Say, the attraction is strong.
French? No, Laura just
Well, what do you mean? You get French order?
You just said it goes with negative value.
it's not that simple.
So numeric.
Yeah, maybe it's like this more.
And we have 30 minutes on. And then we didn't quiz. We didn't quiz the live. The live thing.
Magnitude would be great. The number line. Will, you having a good conversation with yourself? Oh, did you? All right, great. Sophia, are you or Grace the spokesperson for the table? Nose goes. Oh, okay, she's going to volunteer. Grace. The energy decreases. Explain why.
I said
Increases? Explain why.
because the atom is getting smaller. So then.
Okay, and this is where we got. I understand Grace saying increases, and I understand that, and I agree with that. Okay? People would disagree with that, though. Grace, what's happening to the magnitude of the number as you go down? The magnitude? It's getting bigger. Which is why you're saying it's increasing. But what's the sign on it? What's the sign on V if it's a proton and an electron together? It's got to be negative. So this is why when you said increase, I agree with that. In math class, though, what's happening to the numbers? On a number line, they're getting what? They're getting smaller. The magnitude's getting larger, but they're negative. Everybody follow on that?
No, but.
Okay, so the next thing I'm going to have you do is I'm going to have you calculate the numerical values. Okay? So calculate the potential energies of those hypothetical atoms. Plug into that. This is the one of the few times I'm going to have you plugging into that equation. K, I give you K, right? You have D in the table. Q1. What do we want Q1 to be? Eli, what do we want Q1 to be? Proton or electron? Proton. So Q1 is going to be what? +1. That means Q2's got to be -1. Go. Calculate those out. If you want to split up the chores, do it.
You get A, you get L and Q. Because you're
Bro, A's already done.
Alex is E and L. Kristen's Q and T. I'm Z. Okay, that's what I said. Yeah, no, I'm doing Z. Yeah, no, you're doing Q and T. I'm doing a lot of it. Okay.
You already have no electricity. I don't care if you're grass. I say because I'm mental.
do me a favor.
Wait, what did I just go to next?
You get for the first one. I think what you do is, to get the equal to the, you do K, which is that equation 1.31 10 to the -6e.
You're not starting yet.
Times top of 1 10 to the -1 divided by whatever distance you want to do.
Yeah. I did easy.
I think I did it right when I got the number 1.
Bro, in your head,
Just negative. He's just negative. Just negative.
It sounds like you have to.
I kind of have about magnitude, just like so. It's more just confusing. Like I understand, it's just I get it mixed up in my head.
So usually, for the way we do this, we're usually just looking for that.
Yeah, that's supposed to be it.
How big?
Okay, I don't need to.
Well, the key would be making sure you're putting the appropriate size. Okay. So if we look at those numbers, the ionization energy, right?
It does include one.
Which one has the largest ionization?
Alex, look, this is bigger than that. 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 Wait, did you think this was bigger than
Which of those A, L, Q, T, and Z, which one has the largest ionization?
Okay, look. So the distance is not bigger than which
Which one?
which we're taking on this.
bro,
So the distance is less. So it takes
It's 10 to the -18.
Yeah, I was
This is
just
the L, it takes
Right. See, that's why I was explaining why we would line them up.
between the
And that's why
and since
this,
they're
I'm going to have all of those have the same X.
so it's negative,
And make that 46
you have to put in a
0 for those two.
and so you put the weight
0.2 0.462. 1.162. Because
Wait. Oh yeah, they speak
what's going to have the largest
the amount of
volume?
energy needed to take the electron.
I understand what you're. I know what you're saying. Actually.
Look, it's and then you find
Do you have your numbers calculated out?
between this because and it goes up. And it goes up because it's supposed to
Calculate all those numbers out first.
and the more interest you need to like make it zero.
I got it.
Times 1 times negative.
Two magnets shoved together.
That's the unit.
Magnets and I shoved.
Oh, okay.
You know, it's not in this. I'm gonna show some more traction.
Yes. No. V equals a negative.
When you pull it apart.
Oh.
Yeah, when you pull it apart, no. No, James, when you pull it apart, there's no attraction. No, you guys are both wrong. When you pull it apart, it becomes whatever.
I understand the math.
Okay, but when you're doing the
I
process,
don't understand the why.
in the process,
I don't
of energy.
I know how to do it, but I couldn't tell you why.
At least, it must at least, it does not.
Like you've been convinced that you can literally
So the force,
back
so the force of your pull must be greater than or equal to the pull of the.
But like why the things are coming out? I
This
have
is EP. This is okay.
We need to go to basic chemistry. No, I don't know. It's just
You guys are all you guys are so
over I flash it feels long, but like by the end of it, once you start doing stuff like that.
it is.
Wait,
What is Wander's outcome? Why do you think Wander's outcome?
what is
I'm 16 the month that I have to sleep
that's long? That's good.
I'm 16
No, because we take Wander's outcome top. If you just remove Wander's outcome.
You go straight to algebra 1 and you go straight to algebra 1 and
If
you
you
are
take
taking
then we're the same level.
We're having to talk about how I'll explain.
You can get you have your purpose.
The essential facility
I like it. I
have a fear.
If I'm not a bad driver, I'm
I am terrified of that. Just
I'll be looking to be nervous around these.
All right, class. I want to show the setup here because because the units confuse some people, and I want to make sure that you understand why the K value had the units it has. In your math classes, you don't deal with units very often. But we've seen, hopefully, that the units are important to us because they are, in our conversions, how we cancel stuff out to know that we ended up with the unit we wanted, right? So if I plug in, if I set up the equation, I'm going to have V equals. Okay, somebody's going to have to tell me K. 2 point what? And its units were joules times picometers, right? Now, because you're lazy?
Yes.
Okay. Hold on. We don't really have units for the charge for our protons and electrons. Okay? I guess you could say the unit's kind of like the sign on it, but it's not really. It's the sign. So I've got one proton and I've got one electron. Everybody okay with the setup there? And I'm going to divide that by 5,000 picometers, because that's the unit for the distance, right? And right now, you can see immediately what happens to the picometers. They cancel out. So our unit for V is going to be in joules. That's why the unit is the way it is for that K value.
I also assume the high school black market, their units are joules,
Oh, wow, that's, wow, that's really
The
great.
JUUL
Yeah.
instead of the JOULE?
Yeah.
Okay. Ava?
I thought that, the J times Cam, I thought Cam wanted us to multiply the distance, and then it just cancel out, so I'm just thinking, why don't you just have the same.
Okay, so you end up with negative, what is it, 4.26? What is it? 6.2?
Yeah.
Whoa. Times 10 to the negative 20. Which is what of V? Or which is what of IE? This is the negative of it. Because the ionization energy is the energy you have to put into as a positive value to remove the electron, whereas V, the potential energy, is telling you what the attraction is. And we've established that attraction has a negative value for V, and the magnitude of that value is going to be how strong that attraction or repulsion is. Ava?
So you add, ionization energy to the.
Exactly. So you're adding energy to that atom to make the electron move away from the nucleus so far that the electron is no longer part of that atom. Everybody okay?